and move on now to Rick Valenta, who's our final presenter, and is going to take us through halos for Mount Isa itself.
There, it's going to work better now that I'm not on mute. Can you see the presentation? Is it doing the right thing?
Yep, perfect.
Good. All right. So I'm talking about the Mount Isa halo, but really what I'm going to be talking about today is mostly work by Matt Painter, who did a PhD here in 2003, but left behind an excellent collection of core that looks at the Mount Isa halo, for about 10 kilometers out from the deposit. We currently have a PhD student, Ali Pachagani, working on. How come that's not working? There we go. So I'm going to do the briefest of geologies because I think probably a lot of you know Mount Isa and also we're behind time and I've only given myself 10 minutes, so I can't rabbit on too much. But yeah, the Mount Isa deposit itself. There's the sort of yellow polygon I've got for it here. It's in the Mount Isa Valley, and this group of rocks here is the Mount Isa group, bounded to the west by the Mount Isa fault, with these green rocks, the Eastern Creek volcanic coming in under, and crystallina block, which actually continues in the subsurface under the actual deposit. And we're sort of looking at an oblique view here where we can see some of I've just clipped out some of the rock units here. There's the Orchid Shale. All of these sections really mark the position of the copper and lead zinc ore bodies. And there's a huge amount more that could be said about that, but that would well and truly use up my 10 minutes before I talked at all about the actual deposit. I thought I'd try and look at this in a little bit of a different way based on some data that's out there. So what I said to myself to start with anyway was to say, well, what if Mount Isa were under 200 meters of cover? So I've just upward continued the mag by 200 meters. Unfortunately, some of the infrastructure associated with the deposit is still there, so there won't be a quiz on where the deposit is. That's where the various smelters and concentrators and things are sitting. But what you can see is that the volcanics are quite magnetic, and you can even see the extension of this magnetic crystallina block. But the Mount Isa groups themselves, the Mount Isa group rocks themselves, are not very magnetic. You can see quite clearly the more linear trace of units that mark the Mount Isa fault. But what I wanted to look at here was just some of the if you did a RAB program, or if you did a drill program, if you were under 200 meters of cover, where all you did was just enough to get through the cover and sample the top of basement, here are some of the values that you would get. So what I've devised here is just a series of these lines here, just a series of drill traverses, and the lighter blue and darker blue lines here are just where you would get 125 parts per million lead and 1,000 parts per million lead. So probably no prizes for guessing where the deposit is. But I guess it shows that there's about a 5 kilometer halo in both lead and a little bit stronger in zinc because it extends a bit further north. Not huge values, but the other thing that you can see, and this is I've not really shown it here, but that the mineralization is very much following along, or the anomalism is very much following along the Orchid Shale, and a less well-defined copper anomaly. And the other distinctive thing about the copper anomaly in comparison to lead zinc is that it extends to the south of the deposit, which is sitting in here. This is basically the trace of the copper ore body. So I guess I just wanted to start with that to show that if you're actually drilling for an Isa type target with a set of broadly spaced basement drilling traverses, those are the sorts of values that you might expect to see in the lithogeochemistry. And these are all taken from Eric Conahan and Company's paper that are summarized in the atlas that's available. But what I now want to pass to is just talk about some of the zoning that you see in the Orchid Shale. So north is to the right in this diagram now, and the yellow zone in here is the trace of the Orchid Shale. There's the ore body roughly, and what we're looking at here is 3 different zoning diagrams that I'm going to look at in a little bit more detail, all taken from Matt Painter's thesis. Yeah, so I'm just going to move on to the next one now. So if we look at pyrite, for example, and what I put in this diagram is a true scale view of this diagram. So what you can see is that we're looking at variations in pyrite content, fine-grained pyrite to the north of Mount Isa, and the right-hand side of this diagram is all the way out to 9.5 kilometers. So it's quite a quite a long way out. But what I'm showing here in this diagram is the actual this same diagram at true scale. So it's very compressed in a horizontal or in a side to side dimension, and very extended with respect to the steeply dipping stratigraphy. But what you can see obviously is that there's a very strong pyritic halo at Mount Isa that extends really particularly in the lower parts of the Orchid Shale, basically almost 10 kilometers away from the mineralization. If we look at manganese, again, what we see is a slightly different pattern, less of an extent in the footwall, but a very strong manganese halo as well that basically extends in an anomalous way more than 10 kilometers away from the mineralization. And we've already talked a little bit about thallium. This is just the thallium halo that Matt Painter has documented for the Mount Isa mineralization. So it goes, really in a strong way in the main mineralized part of the sequence, up to about 6.5, 7 kilometers away from the mineralization. So I guess the main point of all that is that using some of those measures, the halo of the Mount Isa system is large and impressive, which I guess gives you encouragement for looking for a system like this undercover, that you'd have a good chance to intersect it if you were doing a broadly spaced drill program, and importantly, knew where the host stratigraphy was going. The harder part is that if you don't know where that host stratigraphy is going and drilled to the east or west of that line, you may not really see any halo at all, or at least as far as I'm aware, there's not a whole lot of information on it. I just now want to pass briefly to talk about oxygen sulfur isotopes. And what I'm showing here, again, this is from the atlas, and shows mainly a summary of the work done by Chris Waring, which I think is being in the process of being well and truly superseded by Ben Andrews' work, which has a lot more data and a lot more a lot higher resolution. But I'm just going to talk about the information as it appeared in the atlas. And what we're seeing here is the classic pattern associated with the ISO ore bodies, where which is actually opposite of the one that Peter talked about, where away from the mineralization we have these 20 per mil type delta del 18O values, but actually in where the mineralization is, in through here and to the south of the mineralization, we have a significant depletion in heavy oxygen in del 18O. So that's a classic pattern that has been there have been attempts to apply that in exploration. They have been tempered a little bit by, and this is a very small diagram, but what this diagram is taking is all of the oxygen isotope data for the whole Isa Valley, and the x-axis on this diagram, which you have no chance of reading, is basically distance away from the copper ore bodies. And so what you can see is that there is a pattern there, but it's one where if you got a particular stable isotope analysis back, you could plot it anywhere. If you're only considering this data set. And I know that efforts have been made to make it more possible to use this stable isotope information, but it remains a little bit difficult for explorers to apply when the position that an explorer would normally be working in is drilling a hole, getting an analysis, and then saying, what does this analysis tell me about where I am with respect to the ore bodies? You've got a pretty broad range of options there. Matt Painter also documented a pattern in at least the work he did on the northern extension of the iso ore bodies, where there is a decrease in del 34 sulfur out to 6 kilometers or so, and then he documented an increase again. But when you actually look at the data, it's a little bit questionable. So Peter has already talked about these, so I'm just going to touch on them briefly. I'm showing now the elemental data from that same area out to the north of Mount Isa, and what these different colors represent is the blue is within 1.5 kilometers of economic mineralization. The green is 1.5 to 6.5 kilometers away. The yellow is 6.5 to 9.5, and the purple is more than that. And what we're looking at here is variance on some of the I guess metal ratio indices that Peter already talked about. And yes, they certainly work for Mount Isa. Out to about 6.5 kilometers, really. I mean, after that, when you look at these box of whisker plots, it might be a little bit difficult to distinguish anything more than about 6.5 kilometers away. There's the ZX4, which is just slightly different to the one Peter talked about. And Matt also developed a new ISA vector that used germanium, and he maintained was less sensitive to some of the overall variations in lead and zinc content that sometimes make these metal indices not work too well. But again, that ISA vector is probably best out to 6.5 kilometers, though arguably can be chased a bit further out. So I've pretty much used up, or getting close to using up, my time and eaten 15 minutes into our discussion time. But what I wanted to show here was just the summary of all of that information. And I stole the idea to try and show this information in this way from the CMIC Footprints project, where I think they did a similar thing for it might have been the Athabasca Basin uranium deposits. So what we're looking at with these different bands here are the copper mineralization in green, lead zinc mineralization, which is really sitting over top of and adjacent to the copper mineralization, and then 1.5 kilometers out, 1.5 to 6.5, and so on, and then just different I guess different criteria you would use to try to place yourself in this framework once you had decided that you were within a sequence that could host such mineralization and potentially laterally displaced from it. And I guess what you can see, there's a few different things. As has already been pointed out, you see this progression from more iron-rich anchoritic carbonates to ferro dolomite to dolomite as you go further out. There's a I won't dwell on all of these. One interesting observation is that there appears to be an addition of K feldspar in the so-called tuff marker beds that are used to plot stratigraphy in the in the Mount Isa region, you can actually see that when you look at mineralized data or high resolution XRF data of any sort, where the potassium increases outside the boundaries of those tuff marker beds. I guess another one that's worth pointing out is that in the basement, you see this trend in magnetic susceptibility, and this is work that was actually carried out by Dave Lehman prior to and during the Codes Amira project that Peter already mentioned, where sitting under the copper mineralization and the lead zinc mineralization with a known geometry of the Eastern Creek volcanics, in order to make the magnetics fit that geometry, you have to make them lower magnetic susceptibility than their equivalents elsewhere. So the alteration associated with the copper appears to be magnetite destructive. And then there's a whole range of other, I guess, indicators that I won't all go through here, including, it has to be said, just straight looking at looking at copper, lead, and zinc values as at least a subtle indicator of the presence of mineralization. So I guess that's really I've got a bunch of other things in the presentation that we'll put up when we put up these talks, but I'll probably stop my talk there, other than to say that we're using this reservoir or this I guess set of drill core that covers this halo, and as Peter suggested, going back and applying some of the techniques that we can use to try to get more indications of the presence of the halo that might be collected in explorers data sets that you have now. So we've gone back and used done TerraCore analyses of all the drill holes that I've shown as part of this, as well as Mineralize, and we'll be continuing to do another a series of other investigations of that resource in order to try to enrich the amount of information that we can get about that halo. And the watch this space picture I put on here is Ali Parchagani, who's the student who's working on this. He's still at a relatively early stage in his PhD, but it's I think it's going to show up some really interesting things about this halo. So I'll leave it there, and thanks for your attention, and to all the speakers for the last set of talks.
Thanks, Rick. That's a pretty good summary of one of our best known, best loved deposits. There's been a flurry of question and answer while you were talking. So Peter and Coralie and others have been answering some questions online while that was going on. So thank you for doing that. If anybody has a question for Rick, please pop it in now. And I think there's one just there. John Huntington would like you, Rick, to comment on the role of talc in the silica dolomite alteration regime.
The role of talc. I could comment on the position of talc. That part's easier. So there's a zone that marks the boundary between the and you probably know this, John, but that marks the boundary between the silica dolomite system and the lead zinc system, that in a lot of places is marked by an increase in pyrite, an increase in thallosilicates like stilpnomelane, chlorite to a certain extent, and certainly talc as well. And I only presume that the talc is partially related to an alteration product from dolomite in the sequence and associated with the silica dolomite. But it's definitely an alteration mineral that is coming in synchronously with the silica dolomite alteration, and sits at the boundary between the lead zinc dominated mineralization and the copper dominated mineralization.
John says, yes, that's what he meant. So good job. Ben Andrew also says, thanks, that was really interesting. And other than that,
Can I ask
don't
a
know.
question?
Oh, please do.
Seeing I've got the microphone. Rick, George, Ernest Henry, sorry, not Ernest, Hilton George Fisher system. Has anyone repeated Matt Painter's approach south of George Fisher Hilton, just to see particular oxygen isotopes, but all the other indices?
I suspect they may have, but I don't have that information. And I know that there's work going on now that I'm not really too familiar with that may well be doing that. It's often something that I've wondered about, because Matt's work really extended all the way north to just south of the transmitter fault, which should really be, which is well and truly closer to George Fisher than it is to Mount Isa. It's hard to look at the data he put together, though, and point to something and say, well, this looks like an indication of the George Fisher system starting again. So it really feels like it's starting again to the north of that sort of northwest trending transmitter fault, rather than further to the south. But yeah, Richard Lilly might be able to comment on that. I know he's involved in some of the, if Richard's
and I
still
should say
online.
you've made my day, because it's the first time I've seen that AI stuff that Matt put together that's actually been used and it worked.
Yeah.
Awesome.
Yeah, it worked very well.